Hi everyone. In today's video, we will explore a bit more about strides, padding, dilated and transposed convolutional methods. In the previous video, we were able to derive that for any matrix of size n cross n, a kernel of size f cross f, the output matrix is supposed to be of this size, n minus f by s plus 1, the floor of it cross n minus f by s plus 1, again the floor of it. This is the size of the output matrix. Also, the example which we considered, we were able to say that the stride is considered to be 1. But what exactly this stride means is what we will be covering in today's video, and we will be also making an attempt to see how we can change the stride parameters to reduce the feature matrix extracted from the image. So coming back to the same example which we were having the last time, this was the 6 cross 6 matrix I was having previously, and from the video 1 only, this was the convolutional kernel which was there. Now we say that for convenience sake, the stride is considered to be 3. Now I will just plug in the values in the formula to say that n is going to be of 6, f is going to be 3, and the stride s is going to be 3. And on doing so, we are supposed to get an output matrix of shape 2 cross 2. Now this is exactly the output matrix is supposed to look like, which will mean that if we input a matrix of size 6 cross 6 on applying this specific kernel of size 3 cross 3 along a stride of size s, we are supposed to get an output matrix which will look like this. So what exactly are these terms h11, h12, h21 and h22? How exactly these terms are derived? This is what we are going to explore in depth. So yeah, so we have this matrix over here A, which was the input matrix, and since the kernel is of size 3, we are going to consider the first submatrix of size 3 cross 3, which will remain the same for the calculation of H11. So we will consider these 9 elements, which is the first submatrix, and write it over here 3, 2, and 7 from the first row, and 4, 1 and 1 from the second row, 8, 2 and 0 from the third row. The rest of the values 1, 2 and 2, this 1, 2 and 2, then 2, 1, 2 and 2, 2, 1 are exactly what we have in the kernel which we have, and we calculate the dot product as we did previously and then obtain the first value, that is the h11 as 52. So the calculation of H11 seemed to be pretty easy over here, and it didn't matter whether we have a stride of size 3 or 4 or 1 or no matter what. So the H11 calculation is pretty straightforward. Now we will see how we are able to calculate the value for H12. Since we have a stride of size 3 over here, and since we have to calculate the value of H12, we start from the first value which we calculated, like 3. This is the first value which we calculated. Mark it as 1. Then move a step to the right. Mark this value as 2. Then move a step again to right. Mark this value as 3. And the next value which we obtain is exactly what we are going to consider for the submatrix selection. So we were able to get a stride of 3, and then the next value is 1, and the next value is 6 and 3. So this submatrix of size 3 cross 3 is going to be considered for convolution. So initially when we were at h11 calculation, we were able to consider this submatrix specifically, and we were able to apply the kernel on this submatrix and obtain the value of 52 over here, which was h11 only. Now for h12, since we have a stride of 3, we will just move 2 units till the time we reach 3, and the value of the submatrix henceforth will be used for the calculation. So now We proceed further and then calculate in the usual way, like I consider 1 over here, 6 over here and 3 over here from the submatrix selected over here. This is the first row. The second row of 0, 9 and 8 is selected, and the last row of 1, 2 and 4 is selected. The usual kernel values get multiplied and the dot product comes out to be 54. So we were able to calculate the second value of the first row of the output matrix. Now we were able to calculate these two values using a stride of 3. We are going to apply the same logic when we are iterating downwards. So we will be using the same logic row wise as well while we perform the calculation of H21. While for H12 we were sliding column wise with a stride of 3, we can stride row wise as well for the calculation of H21. The stride will remain the same whether it is column or a row. It is going to be performed in the same way. This is how the calculation of H12 is performed. So we were over here, the first row for calculation of H11 and H12. We move a step ahead, we come to 2. We move a step ahead again, we come over here to 3. And then whatever is there after step 3 is considered as a submatrix. So this is exactly how the submatrix is considered. So we put the values over here 5, 6 and 0 from the first row, 0, 5 and 4 from the second row, 4, 6 and 2 from the third row. We do the dot product with the kernel and we get the value as 52. Likewise, when we are going to calculate for H22, we are definitely going to consider these three elements as the submatrix from the given input matrix, perform the dot product as we were doing with the kernels, and obtain the value as 54 over here. Eventually, the output matrix comes out to be like this. So for a given 6 by 6 matrix, so we had a 6 by 6 matrix with the kernel being 3 by 3, and we were able to apply a stride of size 3. We were able to generate an output matrix H of size 2 by 2. So this is the output matrix generated as a result of the convolution performed from a given input matrix, kernel, and a stride. So in many cases, we want the input size and output size to be equal. So in those scenarios, we do padding, and padding ideally means adding extra layers of zeros along the edges of the input before we perform the convolution. Now, how many layers of zeros to be added is given by a formula which is looking like this. So this is the formula which we consider. Here the filter is of size f cross f. The input size is of n cross n, and this n cross n is before applying padding. And we want the output size to be n cross n as well. So whenever a padding comes, then the input and output sizes are same, but we need to actually pad it with zeros. So a padding with 0 ideally happens like this. Like if in the previous scenario which we had a kernel matrix of size f cross f is equal to 3 cross 3. Then we could do a padding of 3 minus 1 by 2, which is equivalent to 1. So this will mean that we can apply just one layer of pad across the edges. Like this is the top edge. We apply one layer of pad. The right edge, we apply another layer of pad over here. Likewise, in the left edge, we are applying another layer of pad, and at the bottom edge, we are applying one layer of pad. So on doing so, the dimension of matrix was increased to 8 cross 8. Now if I apply the usual formula which we had previously, that if the now the matrix is of size 8, the kernels are of size 3 only, and we consider the stride of s is equal to 1, then the value of the output size is going to be n minus f by s plus 1, and definitely if I apply the float to it, it is going to be 6. So now we are in a scenario that once we enter an input image of size 6 cross 6 by applying padding with respect to the kernel which we are supposed to use. We are able to get the output image of the same size as input, which is 6 cross 6. Now, if we want to keep the discussion in a very simplistic terms so as to not mess up with the notations which we developed previously, this n over here, which I considered, is usually considered as n plus 2p while we calculate, and this is exactly what is happening. We had the value of n equal to 6. I'm just breaking it. Yeah, n equal to 6. Now n plus 2p is equal to 6 plus 2 into 1. The padding was 1 only, which is 8. Now either we can say that the input size of the padded image is 8 cross 8, or we could just maintain that the input size of the image is going to be n plus 2p cross n plus 2p. In either of the cases, the formula will remain the same and the output image is going to be the same as the input image. So having done all our discussion on padding, strides and kernels, we can summarize that the kernels are feature extractors and we may need to train various kernels in the feature extraction process. Some of them may detect depth, some may detect vertical edges, some may detect horizontal edges and so on. Hence, the number of kernels may be usually greater than 1 while performing the convolutions. In such cases, the output image size is given like this. So this is how the input goes. We consider a batch in our example as well from the previous class. We considered the batch as 1 because we were inputting just one image. We consider the width, we consider the height and the channel is like 3 RGB, or if it is a black and white it's 1 only. We consider a kernel kw cross kh, or in layman terms we can also consider f cross f as well. This is also perfectly fine. And since we just spoke that we may need different kernels to be used for different purposes, we assume that this is the number of kernels we are needing. We may need around 10 kernels, we may need about 100 kernels, we may need about 5 kernels up to the model development process really. So for example, if I just need to extract three things, maybe a vertical edge, a horizontal edge and the depth, we need just 3 kernels out of it. But if I just need just one kernel to detect the edges properly, so we just be needing just one kernel. So C out will be equivalent to 1. And the kernel size is kw cross kh. And on doing so and applying the same formula as we did previously, this is exactly what we are supposed to get. So we are supposed to get the same batch size. Like if I enter a batch of one observation, I'm going to get a batch of one observation only. The updated width, which is given by this formula, exactly similar to the one which we used previously, just that n and f are replaced by w and kw. Rest everything remains the same. The height is, so the height is going to be replaced by this formula again. Again the same formula, just the notations being introduced. And the last thing will be C out, like the number of features being extracted. Like whether if I have to extract like 10 features, then I will be getting 10 such width cross height matrices outputted. So this is just a generic formula of how the input and output in any of the frameworks, let it be TensorFlow or Torch, works like. So we will definitely need a batch, a width, height and channel. Channel could be anything, RGB format, that will go as an input. But what comes out as an output is the number of kernels which are used for feature extraction steps. So we will now proceed with one typical way of performing a convolution called as the dilated convolution. It uses all the concepts of strides, padding, kernels that we have learned till now. But to understand this concept completely, I followed this paper on a guide to convolutional arithmetic for deep learning. This paper is very simple and the entire process of performing a dilated convolution is explained in a very simple method over here. So this is exactly how it was explained, and the visuals actually helped me to get a hint of how the dilated convolution is happening. I will provide a link to this paper in the description, but let's consider the same numerical example which we were doing to understand how it works. But before doing that, let's put things in an abstract way, taking hints from the paper I just referred. So over here, let's assume that we have an input matrix of size n cross n. We have a kernel of size f cross n. We do a padding of size p. The stride is of s, and there is a dilation rate d. What exactly is this dilation rate? I will come to it in a minute. But as of now, just assume that this is one constant value which will be given whenever we are supposed to perform a dilated convolution. So we consider the formula where n plus 2p is the padded input, and whenever we have to find the output, whenever a padding of size p is done for a kernel of size f, we go by this n plus 2p minus f by s plus 1, and then there is a floor function being applied on top of it. But as of now, we have something called as a dilation as well. Just to accommodate the dilation, we just subtract this term from the numerator. So this will mean that f minus 1 into d minus 1 gets subtracted in the usual formula for the output shape. And in our scenario, where we were having something like this, that the size of the input image is considered to be 6 and was 6, we considered f as 3. This was given, and this is exactly what we had been considering till now. And we consider that the stride is 1 for calculation ease, and we consider a dilation rate as 3, and we also consider the padding to be 1 over here. So we don't consider zero padding, which we did in the video 1. We consider padding with some value like p is equal to 1 over here, and this is pretty obvious because since f is 3, the padding will be equivalent to f minus 1 by 2, which is equivalent to 1 only. So we do that, we plug in all these values in the formula we just mentioned over here, which was this. Yeah, we do all the plugin, and then we conclude that the size of the output will be equal to 2 cross 2. So we put n as 6 over here, p as 1 over here, f is 3 over here, f minus 1 as 3 minus 1, and d minus 1 as dilation rate was 3, 3 minus 1, and this plus 1 comes as is because it was there in the formula, and then we get the size of output as 2 cross 2. Now we know that if we have to perform a dilation with padding, strides, input, and kernel, we are supposed to get an output which looks like this. Now let's consider the same numerical example which we had been considering till now, and try to figure out how the values of the matrix H, which will be the 2 cross 2 output matrix, will be calculated. We first do the padding of the matrix, which is this. So this AP is the padded matrix. We had the original matrix, and then we did the padding with p is equal to 1, which will mean that the left, right, top, and bottom all got padded with zeros. And on doing so, the updated size of the input is going to be A8 cross 8. Now let's calculate the submatrix which we consider. Usually when we are supposed to consider a submatrix, we will consider something like this. Like we usually consider a submatrix like this and do the dot product of the kernel with it. But since over here we consider something called as a dilation rate, we will have to select the submatrix accordingly. So the first value is this, and since the dilation rate is 3 over here, so we write the first value as A11 over here. This is how we are calculating the submatrix. Now the dilation of 3 means we will take two jumps, like from here till here, here till here, and then say that the next value is going to be the next value of the submatrix. Now I take a jump again, and the value which follows is going to be the value of submatrix over here. Now this is how the dilation is working. So the only difference between a stride and dilation is stride happens after a convolution dot product is performed. Dilation happens in the feature extraction steps only, or I can say the input value extraction steps only. So having said that, the first row is pretty much sorted out. Now let's try to understand how the second row will be sorted. So since a dilation rate, so I always have to remember that d is equal to 3. So this entire jump happened only when the d was 3. Now we will do the same operation row wise as well. I jump over here, I jump over here, and this is the value I got captured. So this is A41 bar, A41 dash I should say. So again we apply the same logic. I jump once, I jump twice, and the next value gets captured, which I write over here. And then I jump once, I jump twice, the next value is written over here. Now this being done, we move a step below. I jump once, I jump twice, and the next value is written over here, which is A71. Again, this will be written and this will be written. So this is how I am able to extract the first submatrix. But we are only half done because we have to perform the convolution operation as well. So to perform the convolution operation, we multiply the matrix values, the submatrix values with the kernel values, and we obtain this. So this was the values which we were able to extract. So A11 dash was 0, A14 dash was 0, A17 dash was 0, and all the values were taken from the matrix only. And then the H11 comes out to be 70. So let's review what we exactly did over here. So instead of considering a continuous segment of an image, we considered every other pixel for performing a dot product in the convolution. So we are not considering all the elements together. We are considering every third element from this beginning for the calculation of feature generation. We proceed further and then we calculate the H12. Now how we are going to calculate the H12? So we first know that we started with A11, which was this. Now we need to go somewhere after performing the first calculation. Here we will go up and see what is the stride exactly we have taken. We have taken a stride of 1 unit, which will mean that the next value is supposed to start from here. So let me clear up this completely so that the explanation becomes a bit easy for the calculation of H12. Yeah, so here we started with this point. Now we have a stride of 1 only. Then the next value should be starting from here because we were having a stride of 1. If we had a stride of 2, then the next value would be starting from here. But since we don't have a stride of 2, we have a stride of 1. The next value starts from here. And then we calculate with the dilation factor being 2. Now I start from here. I jump 2 position here, here, and the third value we pick up. So this is how I am writing it. I12 dash, I15 dash, and then over here as well, I jump once, I jump twice, and the third value gets picked up. I18 gets picked up. And the usual calculation remains the same. This I42 means A42 and A72 gets picked up in the rows and columns. And once A42 gets picked up, we can pick up A45. Again, the same logic. Jump once, jump twice, the third value gets picked up. Again, jump once, jump twice, the third value being picked up, which is A45 dash and A48 dash. Again, A72 is over here. Jump once, jump twice, third value picked up, which is A75 dash. Then again, jump once, jump twice, the third value gets picked up, A78 dash. We put all the values over here. This is the submatrix we are considering for the convolution task. And then we multiply it with the kernel to obtain the value as 33. So first of all, look at what all values we have attained till now. So we were supposed to get a 2 cross 2 matrix. We are able to capture the first row only. Like H11 we are able to capture, H12 we are able to capture. We are yet to capture the second row first column and second row second column. In order to do that, we should remember that we had a stride of value 1, which will mean that if I started from here, the next value for which the computation needs to be done should be over here. So we start from here. For H21 calculation, we proceed in the same way. Jump 1, jump twice, the third value gets selected, which is A24 dash, and then once twice and the third value selected, A27 dash, and so on. So ideally, these are the values which will be getting selected. This and this, and then this, and this. So we do that, and we apply the same dot product with the kernel and get the value as 28. Again, we slide 1 unit ahead of A21 dash to calculate the value of H22. So on putting everything together, this is the output matrix which I am getting, which is like 17, 33, 28, and 22. This is the output matrix which we will be getting on applying a dilated kernel with dilation factor being equivalent to 3 and the other terms being exactly the constant, or the dilation rate being equal to 3. So this is the output matrix we are getting, and this pretty much sums up how a dilation works. We will take a small numerical example which I was able to get from Chegg and try to solve it. So this is exactly a 7 cross 7 matrix which is given to us. And we are also given a 3 cross 3 convolution kernel. So let's assume that this is K and this is A as per our notation. We do have a zero padding, which will mean that this P is equal to 0. Over here, zero padding is mentioned, and the 3 dilated convolution is there like we did previously. Here as well, D is equivalent to 3, and they just want us to find the value of this 1 1. Now first of all, let's try to figure out what the output size is going to look like. So over here, if I just use the formula which I just mentioned previously, N is 7, F is 3, P is 0, D is 3, and S is 1. We have assumed that because if nothing is given, a stride of 1 is being used. Now, if the output size needs to be determined, it will be this formula, n plus 2p minus f minus 1 into d minus 1 divided by s plus 1. The same formula we were able to get it from the paper which I referred. And just we will do the plug and play of the values to conclude that we are just going to end up with a scalar value of a matrix. So that's the only thing we are going to end up with, and that's exactly what is asked in the question. So we go over here and then first try to find out the dilated convolution. So just look into the matrix and it will be pretty easy for us. We select this, we move 1 unit, 1 unit again, the third unit gets selected, 1 unit I move over here, 1 unit I move over here, the third unit gets selected, and then 1 unit I move over here, 1 unit I move over here, third unit, and 2 units later this will be getting selected, 2 units later this will be getting selected. Again, I slide or I choose the dilation factor of 3 and get this, and this. So the ones which are circled are exactly the value of pixels to be taken in our input matrix, and that's what exactly I have written over here. And I get the submatrix and I know the kernel which is given to us. I perform the calculation and obtain the value as 1. That's it. So that concludes the question which I was able to get from Chegg. So the question was pretty straightforward. A matrix was given, a kernel was given, and it was assumed that there is no padding and 3 dilated convolutions are there. And we just put an assumption that the stride is assumed to be 1, which over here won't be making much of a difference though. So we proceed and we get the result as this 1. So that sums up pretty much how a dilated convolution works like. So we will now proceed with another convolution method called transposed convolution by following the exact same paper that we followed while understanding the dilated convolution. we will be able to understand the concepts of transpose convolution arithmetic in a much better way. The entire convolution operations in the presence of strides and pads are quite easily explained over here. I have used much of the formula from this paper, and the visualization did help me in understanding how a transpose convolution works. So just for the sake of simplicity, I am going to consider a matrix of size 3 cross 3. So here n is of size 3 and we have a kernel f of size 2. And in this case, where we don't have any padding and the stride is just equal to 1, we will get the output of size n plus f minus 1 cross n plus f minus 1. In our scenario, it will be 3 plus 2 minus 1, which is equal to 4 cross 4. So we know that we are going to get a 4 cross 4 matrix, but what exactly are the values which will be there in the 4 cross 4 matrix and how they are calculated? This is exactly what we study over here. So this is what we do. We take the kernel. First of all, we initialize a matrix A with all values being equal to 0, like over here, like all the values are 0 over here. Then we take the kernel as it is and write it over here, like 0 I write it, 1 I write it, 2 I write it, 3 I write it. So all the values of the kernel, 4 values of the kernel I write it. And now I take the first element of the matrix A and multiply with the individual values of the kernels, right? So I take 1, multiply with 0, I get as 0. I take 1, multiply with 1, I get as 1. I take this one, multiply with 3, I get 3. I multiply with 2, I get as 2. Now this is how I get one matrix, but I have to calculate 9 such matrices. Now let's proceed with calculation of the second matrix. I do the same thing, like I take the kernel and write it over here while initialize everything else to 0. And let's see what is the second element or I12 over here, which is 3. Then I multiply all the elements of the matrix which I have written with 3 to get 3 into 0 as 0, 3 into 1 as 3, 3 into 3 as 9, 3 into 2 as 6. Now we proceed further and we do the same operation, that I write the kernel values over here 0, 1, 2, 3, and then hunt for the third value of the matrix, which was 2 over here, and I multiply it completely with 2 so as to get the values like this. Sorry for that. Yeah, like this. So I multiply 0 with 2, I get 0. I multiply 1 with 2, I get 2. 2 into 3 will get 6 and 2 into 2 will get 4. I proceed further a step and then I come to the part of the matrix A where the value is 2 over here again. So the value is 2. So I will be writing the value of the kernel in the space which is given and multiply individual elements by 2. And on doing so, the A4 kind of looks like this. So this is how I am getting it. So I just write the value 0, 1, 2 and 3 and multiply them with 2 while all other values are 0. So I do this step for all the 9 such places which could be possible from the matrix. And since we have got values from A1 to A9, we add them eventually. So all the 9 matrices we have got of size 4 cross 4, we add them, and then the final output which we are getting is the output matrix of size 4 cross 4 as we have thought, and this is the outcome of transposed convolution applied on a matrix of size 3 cross 3. So over here, unlike the previous convolutions where the output size is either less than or equal to the input size, we see that the output size is actually greater than that of the input size. So we had an input of size 3 cross 3. Now we are getting an output of size 4 cross 4. Now we can also consider the concept of stride over here, and that will be pretty simple. Whenever we consider the concept of stride, the output size is going to be S into n minus 1 plus f. So we considered a stride of 2. The output size came out to be 2 into 3 minus 1 plus 2, which is equal to 6. So we should be having a 6 cross 6 matrix as shown over here. And the calculation is pretty simple. I take the first element of the matrix. Let me paste the matrix here for understanding. So yeah, this is the matrix which we are having, and this is the kernel which we are having. So since we are considering a stride of s is equal to 2, this is how we are going to perform. So we take the kernel and I write it as it is and multiply with the first element, which comes out to be 0, 1, 2, 3, the kernel as it is. Since we are considering a stride of 2, we are not going to populate the element which we used to populate from here, but we are going to populate a step after that. So we take a jump of 1 and then we populate it. So this is what we are going to populate with. So we take the kernel, multiply with 3 completely, so we get this. Now after that, again the stride is of 2, so we take a jump and the next value gets calculated. So the next value being calculated will be like 2 multiplied with the kernel, which is 0 to 64. Now the same applies for the row sliding as well. So we were sliding column wise for calculating the top 3 values. Now we will slide row wise. Since the stride is 2, so we will stride 1 and then the next value gets calculated, which is this. Like I multiplied this 2 with 0, 1, 2, 3. Again I multiplied 5 with 0, 5 with 0, 1, 2, 3 to get this, and I multiply 6 with this kernel to get this value, and so on. So eventually we are going to get a matrix of size 6 cross 6. So the only thing which one has to remember while performing a transpose convolution is the fact that if the input size is given and the kernel size is given, no stride is given, this is exactly how the formula for output is going to look like. But in case there is a stride given, this is exactly the formula one has to use for calculating the output in presence of stride. In both the cases, one has to observe that the size of the output image is significantly higher than that of the input image. So unlike all the previous convolutions, it gives the output image of a size higher than the input image. So that's it for this video. In the next video, we will be talking about 1D convolutions in detail. Thanks for your time.